fusion splicing is the act of joining two optical fibers end-to-end using heat. The goal is to fuse the two fibers together in such a way that light passing through the fibers is not scattered or reflected back by the splice, and so that the splice and the region surrounding it are almost as strong as the virgin fiber itself. The source of heat is usually an electric arc, but can also be a laser, or a gas flame, or a tungsten filament through which current is passed. Process: the process of fusion splicing normally involves using localized heat to melt or fuse the ends of two optical fibers together. The splicing process begins by preparing each fiber end for fusion. Stripping the fiber. Stripping is the act of removing the protective polymer coating around optical fiber in preparation for fusion splicing. The splicing process begins by preparing both fiber ends for fusion, which requires that all protective coating is removed or stripped from the ends of each fiber. Fiber optical stripping is usually carried out by simply passing the fiber through a mechanical stripping device similar to a wire stripper. Otherwise, a special stripping and preparation unit that uses hot sulfuric acid or a controlled flow of hot air is used to remove the coating. Under a process patented by Edward J. Forrest, Jr. and assigned to Illinois Tool Works, Glenview, Illinois, there is a timed chemical removal process that does not require use of hot sulfuric acid or hot air. The process is patented as a solvent capture method primarily conceived to remove the matrix that holds individual fibers and creates a ribbon fiber. This same procedure can be timed to remove not only matrix, but also coatings and claddings. Cleaning the stripping and cleaving tools is also important. Cleaning the fiber. The customary means to clean bare fibers is with alcohol and wipes. However, high-purity isopropyl alcohol is hygroscopic, it attracts moisture to itself. This is problematic as IPA is either procured in pre-saturated wiper format or in containers ranging from USA quarter-gallon to drums. From the host container the IPA is transferred to smaller more usable containers. The hygroscopic nature of IPA is such that the highest quality at 99.9% is also the most hygroscopic. This means that moisture absorption into both the host container as well as the actual user's container begins with the time the original container is opened and continues as amounts are transferred and removed from both. A 2003 laboratory study by ITW Kintronics noted that 99.9% IPA began to absorb moisture within 15 minutes. Since there is no provision to deter this unique quality of IPA makes it less desirable than chemicals such as HFE 7100-based products or precision hydrocarbons. There is work being done to qualify aqueous-based cleaners for this application. Cleaving the fiber. The fiber is then cleaved using the score and break method so that its end face is perfectly flat and perpendicular to the axis of the fiber. The quality of each fiber end is inspected using a microscope. In fusion splicing, splice loss is a direct function of the angles and quality of the two fiber end faces. The closer to 90 degrees the cleave angle is the lower optical loss the splice will yield. The quality of the cleave tool you are using is critical. Splicing the fibers. Current fusion splicers are either core or cladding alignment. Using one of these methods the two cleaved fibers are automatically aligned by the fusion splicer in the X, Y, Z plane, then are fused together. Prior removing the spliced fiber from the fusion splicer, a proof test performed to ensure that the splice is strong enough to survive handling, packaging and extended use. The bare fiber area is protected either by recoating or with a splice protector. A splice protector is a heat-shrinkable tube with a strength membrane. A simplified optical splicing procedure includes characteristics of placement of the splicing process. Checking fiber optic splice closure content and supplementary kits. Cable installation in oval outlet. Cable preparation. Organization of the fibers inside the tray. Installing the heat-shrinkable sleeve and testing it. Cleaning the fusion splicer. The fusion splicer is a magnificent instrument that has evolved from massive, cumbersome chassis to handheld and convenient benchtop designs. There are two important areas of cleaning concern. 1. The first is simple cosmetic cleaning of the surfaces. These include the screen, keys and chassis of the device. Always select non-paper, low-linting materials for any and all these tasks. Never use cotton products as they also can lint as wallpaper. 2. The second areas are the actual alignment mechanisms. These include A. V-grooves, B. Fiber holders, C. Lenses, D. Mirrors, and LED surfaces. Consult your manufacturer for recommendations. Hardware. The basic fusion splicing apparatus consists of 2 fixtures on which the fibers are mounted and 2 electrodes. These fixtures are often called sheath clamps. Inspection microscope assists in the placement of the prepared fiber ends into a fusion splicing apparatus. The fibers are placed into the apparatus, aligned, and then fused together. Initially, fusion splicing used nichrome wire as the heating element to melt or fuse fibers together. New fusion splicing techniques have replaced the nichrome wire with carbon dioxide lasers, electric arcs, or gas flames to heat the fiber ends, causing them to fuse together. The small size of the fusion splice and the development of automated fusion splicing machines have made electric arc fusion one of the most popular splicing techniques in commercial applications. Alternatives to fusion splicing include using optical fiber connectors or mechanical splices, both of which have higher insertion losses, lower reliability and higher return losses than fusion splicing. Governing standards, ANSI 455. See also, optical fiber, single-mode optical fiber, multi-mode optical fiber, fiber optic communication, bending. References. Methods of removing matrix from fiber optic cable. Patent 7,125,494. Further reading, Introduction to Fiber Optics by John Crisp, Fiber Optic Fusion Splicing What? How? Why? By M. Anderson, How to Precision Clean All Fiber Optic Connections. Edward J. Forrest, Jr. www.amazon.com www.createspace.com/51730668